Thanks. So it's like always good to be back at CWI. It feels very, coming back at home, stuff like that. So yeah. So what I'm going to present today is something very simple. So the good thing of this presentation is that I'm going to talk about a problem that all of you have seen in your randomized algorithms course.
Never took a randomized algorithm course.
Oh no, yes, in some other course. Sure, it's like
you pretend.
Yeah. And I'm going to present a different proof of what you guys had seen, and it will be very simple. Yeah. Okay. So this work is joined with Kuldeep, Meel, and Vinodchandran. It's a collection of some 3 or 4 papers, and somehow Donald Knuth pops his head up somewhere in the middle of this talk. Okay. So we are talking about the streaming algorithm setup. So what is the setup? So you have a stream of items coming, and a stream of items coming meaning that once an item comes, you do something with that item. You can store it. You can store some information about the item. You can do whatever you want to do with that item. But then the item goes, and when the item goes, it is not coming back, and you cannot go back and do something on that. And the main idea is to compute something about this stream. So there is this huge stream, and you want to compute something. And the main focus is to reduce the amount of space required. That's the standard stuff. So the optimization problem usually is about the space complexity. So I'm going to introduce another one. It's like called the update time complexity. This is the time for which the item you are holding on to before you move on. Now I will explain this thing more clearly in a particular example. So in this talk, we will be mostly focusing on this case of stream of sets. So you have a stream of sets coming, and the job that we are interested in is to compute the size of the union of the sets. And I want to compute it within plus minus epsilon multiplicative approximation with high probability.
Stream of sets, as in now we are not looking at items, but
one item is a set. Oh. Okay, now how is the set given? Okay, let me do one simple thing. Like, look at the sets of size 1. So this is the most classical problem, and we will be spending some time on that problem. This is called the F1 estimation problem or element distinctness problem. So you have a collection of elements coming, and you want to understand how many distinct elements have come. So a typical example that one can think of is that if you have a web page and you want to record how many people visited your web page. You can of course keep a counter for every time somebody visits, but that will not be taking care of the same person might be visiting 5 times. So one option is to store the IP address from which they are coming. That's possibly for a big website, it's a very costly affair. And can we do something clever to, if not get the exact one, but somewhat approximately exact, but while using very little amount of space. Okay, is the problem clear?
So when you say probability, you mean that like, because at every sort of, presumably after every item, you make a guess, and then sort of a delta, 1 minus delta fraction of those guesses has to be within the boundary?
No.
Okay.
No. At the end, you tell a number.
Oh, the stream stops, and then you say,
yes.
Okay, very good.
At the end,
and that has to be correct.
Yeah, what you told is something slightly more
complicated.
More
online. Yeah.
It is like you keep on guessing every time. There are variants of that.
Okay, yeah.
But we will not be
So
going
more
to
static problem. I'm happy.
Yeah. So at the end, you do, And you have randomness, internal randomness.
Yeah, so what is the probability about?
Probability over the internal random points of the algorithm that is.
Okay.
Yeah,
That's
so
total.
at the end,
Not how the sets.
No, the sets and the stream is adversarial.
Yeah.
Sets and the
you
streams are
use a guess,
Yeah.
and with some probability, the guess is correct
Yes.
for all streams.
Yes, yes.
Do we have an idea of what this M could be?
Okay, good point. In general, no, but I will be presenting this stuff where we know it, and then we'll talk about it, how we can get rid of it later on. Okay. Okay, excellent. I'm happy that I'm getting questions. Yeah. So one thing that I have not told you guys is that if I am talking about this element, that's fine, right? The elements are coming, you look at it and done. But what about sets? How are the sets given? Right? How are the sets given, and more importantly, how are the sets accessed? So I'm not going to formalize it till the later part of the talk, but let me give you an example. So this is called this is a famous problem called the Klee's measure problem. The sets that are coming are axis parallel rectangles in d dimensions. And you can think of that we are only interested in integer coordinates. So every set can be specified by just the diagonal points, right? Diagonal coordinates. So they are very easily given. And what we are interested in is the union.
Okay.
So note that if an element, so while an element can be given, a set can be specified in only d times the log of delta amount of space, the total number of points in that each set is exponential in d. So how are the sets given? Okay, we understand. How are the sets accessed? So there is the following things you can easily do with these sets. What you can do is that you can quickly tell me the size of each individual set. That's easy to do, right? I know the coordinates. I know how to calculate the size of a rectangle. That's just a multiplication of some d numbers. I can also uniformly at random pick elements from this set, from any individual set, not from the union, but from any individual set. And if I give you an x, can I check whether that x is in this set or not? Yeah, that membership can also be checked. Right? So in some sense, you can think of that these sets can be accessed via these points. Yeah.
The O d log delta that you're measuring there is the space complexity, is it time complexity?
It is the time complexity.
Maybe switch time complexity.
No, so again, as I told you, that there are two complexity measures that we will look at. One is the space complexity, and one is the update time complexity. So it is the amount of time for which an element you process. Okay, so that did not make any sense if there was a single element, but now it's like a very concise representation of a lot of points, right? A set is a concise representation of a lot of points, and we don't.
Is this element X in N?
No, it's not. It's like X in the yeah, it's a universe.
To check if X is in SI, is I fixed?
No, for any set. For any set. So the stream is a collection of sets, right? Take any set. I mean, and what is the set? Is the axis parallel rectangle, right? Now, if I give you a point, can I check whether this point is in this set? That is easy to check, right? It's a rectangle, so it's like easy to check.
So,
That's
so,
all this set.
so in some sense, you're making the problem even harder. You're saying, okay, we don't get just access to the sets,
Yes.
but we get some succinct description, and we care about things that are fast with respect to the size of the set.
Right.
Okay.
Right.
Okay.
Is this delta upper bound for every SI? Or
This
the
delta?
No, sorry, the bigger delta, the capital.
You can think of this bigger delta is, yeah, it's for every set. Yeah, this is just
These are the things you're going to demand of your sets in the abstract, like that you compute these type of properties.
I would compute this one.
Yeah, but do you use the yellow properties to do that?
I will be using the yellow properties to access the sets.
Yeah, so this is sort of what you demand of the structure of your sets, and then you will give an algorithm.
Excellent. I think we are already seeing half of my talk.
And what is n here?
So forget n. This is not this was a universe.
Small m is the number of sets.
Yeah, so it's like delta to
The length of the stream.
For the Klee measure problem, the yellow stuff is sort of over, right? Because you could just give the 2D numbers, the A's and the B's. So is the yellow stuff really for problems that are beyond the Klee measure
No,
problem?
it is for so the specification can be done here. Okay. Now I am saying that okay, if you are given the Klee's measure problem, so when a set is given, you can do a lot of things with it, right? And I'm going to restrict myself saying that I'm going to access this set only via this set of queries. Okay. So I'm making myself harder, and I show that this is good enough. I mean, maybe you can do something more for this accessible rectangles. And
Now I have a kind of silly question. We know this bound of like how big how the elements in SI could look like,
yes.
but how do I ensure that I sample from SI when I don't have SI any more with me?
No, you cannot. You can sample right there.
Okay. So
When a set goes, it goes.
Goes,
Then you have
okay.
no. I mean, if S1 goes, then you cannot have access to S1.
I see.
When the set comes, that time you can access the set using the samples.
I see. Okay.
So it's just like the membership of.
That last one is the membership. Last one is just a membership. Okay. Excellent. Yeah, so there were some lot of stuff there done, and it was a big open problem for a long time. That can you have can you solve this Klee's measure problem when you have both the space and update time complexity polynomial in D and the log omega, or you can think of this one as polynomial in log of the universe size. Okay, this was the main problem, and I will kind of show that what we will be solving is the Klee's measure problem, and because we are going to restrict ourselves to only these things, we can talk about slightly more general objects, which kind of can work for much bigger stuff.
So this open problem is kind of trying to address this question by removing the dependency of how many SIs I can have, because there's no M.
Yeah, so right now there is no M here, but even with an M dependency, can you do that? So let's say this way. In fact, initial papers that were there, they kind of had a, I would call a kind of a cheating kind of stuff, but they assumed M is equals to N kind of stuff like that.
Yeah, and then the difficulty is that you're only given a succinct description of the sets.
Yes, that's the very point. So if one thing is that we could have just unfolded this set and said, oh, this set contains this set of points.
Yeah, just write that out.
And so let's write down all the points. And it's now a stream of just points. But the issue is that each set contains exponential amount of points, right? So if you just unravel the whole points, then that's an exponential amount of time for which you are holding on to this set.
When you say exponential, now these are continuous sets.
No, but even in the, I mean, if you are looking at the integer points, right?
You're looking at
Yeah, I mean, it doesn't matter. You can just discretize it in whatever way you want.
You say exponential, it's exponential in dimension.
So yeah, so that is the main trick. Putting the D in the polynomial, not in the exponent. Okay. Good. So I will come back to this Klee's measure problem later on. Instead, I will go back to this element distinct problem, which is a much simpler one. Right? There is no issue about accessing and all are not there. Now, this problem is like clear, right? So you have a stream of points and you want to look at the number of distinct elements in that. This is the problem I told that most probably all of you have seen it, because it's a very, very popular problem to look at, although it's a very complicated solution is there. Now, so here is an example of a stream, and it's kind of like you might have the stream where one appears way too many number of times, but the number of distinct elements is just 3. Just if you can remember this example, that will be kind of a useful thing to go back to later on. And we want to do this epsilon delta approximation. Of course, now what is the naive solution? Naive solution is very bad. Is that you kind of maintain a hash table, a large hash table, or basically a kind of vector saying that which element has appeared or not ever. Right? So as soon as an element appears, you goes to there and put a marked kind of stuff. That's a lot of size of space that you have to solve, right? And the goal is to optimize the space complexity. Here, update time doesn't make any sense. Because anyways, what will you do with a single point?
So if we use a radix tree kind of data structure, we should be able to do it in log n, right?
What do you mean by that?
I kind of maintain tree sort of a data structure, which will let me enter the elements based on the binary representation of the elements. And every time I have an element, I just traverse the.
No, you're
tree.
talking about the time to do it, right? But the space, you have to save the whole tree.
Yes,
Yeah, you're still writing down.
I still
That's
have
a massive thing, right?
Yeah.
You want to save the space,
Yeah.
and that's the part. Okay, so this has been there from a long time. 1985, we started with the work of Julia and Martin, and then I think a couple of Gold Prize winning papers have come up on this work. Most famous being the Alon Matthias-Segedis paper. And the crowning jewel is that we now know algorithms where the optimum space complexity is this. It has been really optimized to the last bit, in the sense that, I mean, they have put in a lot of work to make this one class and a lot of multiple, and every possible bits. I mean, in fact, the constants here has also been kind of worked out. Now, many people have told me later on that they have used this problem, they have explained this the algorithm to their class. It's a hashing based technique. Okay? It's not the easiest thing to explain to a undergrad student, because it has lots of this kind of pairwise randomness issues and all of those kind of stuff happen. But that's not the more interesting part. The issue is that if you try to implement this algorithm, it is super slow. Now, why? This is something I am not a practical person, but I got to know is that although it's like a very good algorithm, the constants there, because you are maintaining a hash table and all of those kind of stuff, is pretty horrible. And so this algorithm theoretically is beautiful, but can never be used. Although, of course, this is not the reason why we wanted to look at this. We wanted to look at it from the Klee's measure problem, and the Klee's measure problem this algorithm could not be generalized to Klee's measure problem. So what I'm going to present now is this algorithm, which is worse than what is known, but it's a much simpler problem. So a solution that I'll give you. In fact, it has a M dependency also, which I'll talk about later. But the best part is that it is very simple. It is implementable, which we have done also for some other problems, and it can be extended to Klee's measure. Now, for selling point, you can take Knuth for this one, and like Knuth was like over the moon for some time, and of course, we are very excited about that. Okay, so this is the problem that I'm going to first explain. Now, let me use the board once. So if I have a space, right? So if I have a space like this and ask you to what is the area of this space, how will you do that? Some ideas?
Wait, how is it described to be? Do I have an Oracle access to it or something?
You can have Oracle access to it, say.
That I could like randomly sample and
You can randomly sample. Can you be specific a bit more?
sort of.
Yeah, I'm
You
gonna
know.
start throwing darts at it. I'm gonna start throwing
Yeah,
darts at it.
Well, you are basically going to put it inside a big box,
Sure, yeah.
which you know the area, and throw darts at it and look at how many of the, if you throw 100 darts, how many of them hits.
Yeah, the space is big when it has many points in it.
Right. Now that is very good algorithm, but that only works when this space is comparable to the outside space.
Yes.
If
Sure.
this space is much smaller than outside space, this algorithm will not work.
Or it'll need a very, very long time to hit off it.
Yeah, I mean, like it will be very slow.
You need some good notion of drawing a box,
Yeah.
basically.
Now let me give you another way of doing it. Okay. If somehow I could go over all the points, how, that's a different issue. If I could go over all the points in this space, okay, and for every point, I flip a coin independently and pick that point with probability P. I can go walk over all the points, and for every point I flip a coin, pick it up independently with probability P. At the end, I find that, oh, I have managed to pick up 100 points. Then 100 by P is an estimate for this problem, this measure, this volume.
And why you need P? Why you can just say it was probability 1?
Yeah, you can do it with probability 1, of course, but also you can do it with the other probability, for lower probability also. Now why? See, if P is low, then this number is low. So if this number, this actual volume is say D, and you pick every polynomial with point with probability P, the expected number of points that you pick is D times P. Right? And if P is something like 1 by D epsilon square, or more than basically. Okay. Look at the number of points that you have picked. This by P is a very good measure. It's a simple turn-off. Now, of course, I'm giving a very high level thing because how do you walk over? If you can walk over, then why do you even care about it? So all those things will come. But this is the main idea of the whole thing. Core idea is that in the union of the sets, or sorry, in the union of the, so in the stream, okay, let's look at the elements that we have seen so far. I want to pick every element of that stream, every distinct element of that stream with probability. Okay, so that's the goal. If I can pick every ball or every element, okay, with probability P, then I'm done. So all I need is to, as the stream comes, I want to somehow keep on updating my set of elements that I've picked, such that every element is picked with probability.
Oh,
Is
okay.
the bucket the same as the mean? That's another word.
Yeah.
So you're sort of,
Yeah.
instead of writing down a list of unique elements, you're sort of trying to engineer a uniform sampler of the list of
Right.
unique elements. Okay, very cool.
Okay, so that's the main idea. Like if you can get a uniform sampler of the whole thing. Yes. Sampling and estimation are always the same problem. Now, how do you do that?
Can you tell me again the way you would do it? So if I get an element.
I've
A-
not told you how you do it.
Yeah.
Oh,
I think
okay.
that's gonna
I've
be the
not
hard
told you,
part.
but this is the goal. Okay, the goal is that as a stream comes, every distinct element in the stream would be picked with this probability P independently. Okay. Now let's see. How can you do it? Okay. So maybe the first idea we can think is that, okay, as an element the stream is coming, just blindly pick that element with probability P. But do you think this is a good way of picking every distinct element with probability P? You guys remember this? So this would be the naive algorithm. And you remember the example that was there? Do I have the example? No, I don't have the example. And where there was lots of ones and only 1, 2, and 1, 3, and 1, 4. So the ones are coming too many times. So if it comes 10 times, it is getting 10 shots at getting selected. So it is being picked with the probability higher than P in some sense. But the other problems are being picked with the probability P. So that's not good. So if you pick every element that comes with probability P, then the elements that are coming more will have a better chance of getting in my bin. So not good. Now this is where our first or basically the only idea came. It's like quite amazing, okay? And like after, I mean, when you explain it to people, they're like, okay, it's like, is it really that's all? So say I have a set here, okay? And I have somehow, so this is the set of stream element that we have seen so far, okay? And among them, some of them has been picked with probability P. So this one, this one, this one, this one has been picked with probability P. Now, so one more element has come. And I can say one more set has come also. Now, what's the issue? That this, if I pick every element from this set, so okay, there might be elements here that have already been picked, right? And there's some elements here that are not being picked. So if I now pick elements from this set independently with probability P, then the issue is about the intersection. Like the intersection points getting a higher chance.
Yeah.
So what do? Just think. Every element in this chunk currently has been picked with probability P. I want to do it for the whole thing.
Do I know this intersection?
I don't need to. I have a membership query.
Ah, yes, indeed. Yes. So you can just sort of redefine the probability for those intersection points.
That's one way of going about it, but that's very complicated.
Okay.
Okay. Other way is that look at the point that I have picked already. Okay. These are the points that have been picked, right? I look at among those points that are picked, which of them are in my set, and I throw them away from my bin. Just throw them away. So what happens? At that time, it's basically from this set, every element has been picked with probability. Okay. And now all I am left with is picking every element from here with probability P. And that is possible we can do. And that's it. This is the main trick that is there in the whole.
Wait, and then you sort of induct your way up from this?
I mean, just like
Yeah,
the next
okay.
one comes up, you do the same thing. So this is the other. Okay. So this is written in the form of a set. So when a stream there, so B is the bucket that we are talking about. When an element comes, just blindly throw it away from the bucket. If it exists, if it doesn't exist, anyway, there's nothing to throw away. And then put it in the bucket with probability. It ensures that if a point is in the bucket or not depends only on the last time it has come.
Yeah, so if you observe something again, you immediately throw it away and then you just try again with probability.
Yes.
Okay, very good.
So there's no question of any history being left over.
That's really dumb and it works.
It works. It's like basically this ensures that every element, what is the probability that element is there in the bucket? That depends only on the last occurrence. Even if it is occurred earlier and I have picked or not picked, who cares? Because when I'm after this line, after line 3, it's cleaned up. And that's it. Okay, so that is basically the main crucial idea of this whole thing. Of course, I've not told you a few details. Okay, so anyway, so you realize that by doing so, you can pick every element with probability P. Now, I have not told you what is P. So, see, P is something which you cannot make too small. Because if you make too small, if P is lower than this, you are in a bad shape. You're basically not getting any point and your estimation will be off. If P is large, then the bucket size becomes large. So it's kind of a somewhere in the middle. So you adapt. What you do is, let's say at some point of time, I have my bucket size as size 10 and I have got 11 points now picked. Okay, so in this set, say I have 11 points picked. what do I do? And this is with say probability P. Every element is picked up with probability P independently. So what do? I go to this point that I have already picked within my bucket and throw them away with probability half independently. So some of them get thrown away. This is same as picking every element with probability P by 2. So when I'm hitting the bucket, I reduce P and my size is shorter.
This is such a violent process.
Yeah, and that's the algorithm. That's the whole algorithm. So basically, an element comes, you throw it away. So if it is bigger than, sorry, if it comes, you throw it away, you put it with probability P. And if my bucket crosses a particular threshold, you throw away every element from the bucket independently with probability half.
This is maybe a worse solution, but just to see if my intuition works. I could also just start off with like, geometrically spaced choices for P, and then keep sampling, doing it for each of the like geometrically
Okay,
spaced.
I'll come back to that. There is a way, I mean, we have a later version of this.
Okay.
Does work with that.
Okay.
That's a bit worse than in terms of
Yeah, because
complexity
you pick
wise.
up a logarithmic factor.
Yeah, but it has an advantage also.
Okay.
Yeah.
Your P goes down by factor 2 every time you sort of go over the threshold, right? So
Yes.
what about the second bullet? If P gets too small, you don't have to estimate anymore.
Second bullet.
Second bullet higher.
Yeah, so we will. So the proof that will be required is that P never goes full. Because that's the thing that we will be proving. So that's the only thing that is left to be proven here, right? That with high probability, P will never go. I mean, that's not a very right statement. With high probability, P doesn't go small. Okay, so here is the proof, basically. So say P becomes small. If P at I suddenly becomes less than 1 by epsilon square F0. So that's a bad thing. But let's think about it. What happens there? Why did it go down? It went down because, okay, at that time, every element was being picked with just double of this thing. Every element was being picked with double of this quantity, right? So P was 2 by epsilon square F0. If every element is picked with 2 by epsilon square F0, and the total number of stream size is anyway less than F0, on expectation, how many elements should I have got? It would have been 2 by epsilon square. So we have to now apply a Charnov bound to say that the probability that it is, so expectation is 2 by epsilon square, probability that it is more than the threshold, which is 2 by epsilon square log n, is this one. So it's just a simple Charnov bound. Now I need this log m. So if you see that there is a threshold m there, is so that I can make this probability of it going down at the ith step to something by n, so that I can apply the union bound and say that it never goes down.
Can I intuit this as saying that it's just unlikely that you're going to hit the threshold very many times?
Yeah.
Because you like every time you have to sort of climb back up.
But then there are, so okay, so yeah, again, yeah, this is like some technical stuff. Like even after you get this P to be bigger, there's still a chance of I'm not getting a right answer, right? There's a random process there, and that there's another Charnov that you are getting. So this is the Charnov that I kind of initially talked about. So last one is the initial thing. Charnov, and every element is picked with probability P. What is the probability that you get a good estimate? Now there is a m factor here. It is something that cannot be avoided in this particular algorithm. Yeah.
Is small m the same for all the sets? Like m?
No, small m is the number of the stream size, the number of,
Oh, sorry, yeah.
yes. So yeah, so I have to do a union bound over all the stream length. Okay. And I can explain why m is required, or at least some dependence on m is required because I can cook up, because one thing you can see here is that the value of P monotonically goes down. It never goes up. And that kind of causes a problem. Yeah.
Does it mean you should only care about bad sub M rather than all the bad sub I's?
Bad sum.
Bad sub M? Because P is monotonically decreasing.
Yeah, but maybe it's like, no, I think there's some, so bad sub M will just say that what is the probability goes down below this one, right? And issue is that, yeah, it's like what time does it go down, right? Because we are talking about it that okay, bad sub I is like the place where it goes down. Like, let me give you the example. Okay, think of a set, a same set, the same element. The same element is not a set. A set of distinct elements. They're coming again and again and again.
The same set is coming again.
Again and again and again. Okay. Now what will happen is that you will first go over the first part, first set. Every element is picked with probability P. Then the next one comes, you're basically throwing away everything and sticking everything with probability P. Then again, so and of course there is some probability 1 at some point of time, you'll be picking up every element in this set, right? That's a bad case. We will push the value of P very low. I mean, I don't know that I explained it very well, but there is a reason why the M do appear. Yeah.
Shouldn't, maybe I'm misunderstanding something, but shouldn't it be sort of like bad I is like would I be like the first time that it drops below that threshold?
Yes.
Then you
That's
would,
what the idea.
then you would also need to do the union bound, I
Yeah,
guess, because if you don't, because for bad M then would be defined like it dropped below this, but
Yeah.
you can't
So we
assume you
thought
were
that
above it,
initially we
right?
can do this bad name, like there's only one time you can talk about it and all, but no, there is other reasons why it gets done. Yeah. Okay, so that's it. This gives you so this one. Now, best part of this whole thing is that if you think of it, although I wrote everything for distinct element, I explained everything for union of sets. Right? Because when I drew it for the set, right? It's exactly the same thing. So, yeah. So the good thing of this algorithm is that it is, of course, very simple in the sense that you only need Charnow bounds a few times. It is sampling based. So, what is sampling based? Somebody really pinned me down the other day. So what is sampling based? It basically means that when I am storing an element, I'm storing every details of that element. Okay, meaning I can then retrieve everything information of that element. Is the element in a set or not, the membership queries and all. If you are familiar with the standard streaming algorithm, people don't store the whole information of a set, of an element. They store only a hashed value of it. And that's completely causes a lot of issue. So this makes this one very good implementation. I will talk about implementation a bit later. And it can be extended to the set estimation problem. So before I go into the set estimation problem, let me now formalize it what I started. Okay. So I call a collection of sets Delphic sets if you can access the sets using these three operations. You remember these operations? Because there is the Klee's measure stuff. It's like a set is coming, I can quickly access, quickly meaning order in order log the universe size. I can access the cardinality, I can do the sample and do the membership. Yeah.
I think the cardinality of the sample should be much harder than the membership, right? I mean, in terms of the...
Yeah, but for many things it is easy. Like for example, the Klee's measure, it's easy, right? It's like axis parallel rectangles. You can easily compute this one.
Yeah.
And in fact, I can give you examples. So here are 3 examples, but this Delphic sets are useful. The first one is something that you guys possibly have seen. It's like, you know, DNS, it's order of and. The big question is how do you estimate the number of solutions accepted by a DNS? Each and clause So or of and, right? Each of the and clause gives you a set. And the or basically says that what is the union of the sets. And they are also delphic because they are like, you can, you can specify the sets very easily, check membership, draw random points. Please measure problem, of course. There is also a test coverage estimation problem. I don't want to go into that. I can talk about it separately. It's another very big area. So basically, many of the problems can be modeled in this delphic issue. And yeah, the problem is basically what I kind of explained earlier. Estimate the volume. Now, what about the algorithm? No, there's not that the algorithm is, so forget this one. Yeah, the main idea is same as what I explained for the singleton case. At any point of time, I want to do is that I want to pick every element in the union with probability P. And every element has to be picked up with probability P, and the P should not be too small or too large. Yeah.
Is there any sort of theoretical improvement if you store hashes of the numbers instead of
We
the
have not got that yet. I mean, I will show some open problems. There might be some issues, but this membership queries is something we use quite crucially, right? And hash doesn't allow us to do that.
little errors all over the place?
Yeah. So we have not been able to iron out that stuff. Right. Yeah. Okay, so these are all of the. But there's one trick. Okay, so here, if you think of it, I did explain you how to process. Right? If you have picked up in this is a union of the sets till now. If you pick every element with probability P and another set comes, how do you take union, pick every element of this new union with probability P? But the same thing, right? You throw away the elements from this current set and sample from this one. But there's only one issue. With the element thing, you pick one element with probability P. That's what's easy. Here, how do you pick every element here from this set, probability P? Because these sets are, of course, of exponential size. How do you pick every element of probability P?
But currently that set is with us, right?
Yes, but that will take us, if you have to go over the whole set, all the elements of the set, then that's an exponential amount of points that I have to walk over, right? So the update time will become exponential, not the best thing. So what happens if I had picked every element of a set with probability P?
P times the cardinality.
Yeah.
P times the cardinality would be the expected number. Can you say something more? Can you say this number, what will be the distribution? Huh?
It's very concentrated.
Yeah, it is actually distributed according to the binomial distribution. And we have a way, if I go back, we have a way to sample uniformly at random. I don't know how to sample, go over all points and sample, but I have a kind of a way of sampling uniformly at random. So if I know how many to sample, I can sample it, right? So that's basically all we do.
Okay. So you're sort of sparsely unrolling.
Yeah, exactly. So what we do is that sorry. Yeah, you first, you know SI has come. You know the size of SI. So you know that if I have picked every element from P with probability P, I would have been picking up a number which is distributed according to the binomial distribution. So you first pick the number, how many would I have picked according to the binomial distribution, and then draw this many number of distinct samples from S.
these things you just tested, they're unique?
Yeah, we can test it. Yeah, and okay, we say, okay, what happens if you are doing with replacement, right? But that's coupon collector will take care of it. You don't have to go too far away.
So yeah, you don't actually, you're only interested in the size of B, so it's
Yes.
fine, okay.
All I need is size
Answered my
of
own
the
question.
SIs,
Yeah,
and I need, so here the size of SI is required. Here is where I have using the random access to the sets, and the membership query was before that. And okay, maybe this NI is big. What do? You basically treat it as a bigger one, reduce P, desample, and so on. So these are kind of, I think once you get the idea about the sampling algorithm, these are all of them are like a just wrapping up the whole thing. Okay, so yeah, so this is what we managed to do. We have come up with this algorithm which has update and space-time complexity, this thing. Note that M do appear here, not a good thing. M should not be appearing, but in the literature of the streaming algorithms, many times they kind of assume that M is equals to N, and that's kind of a cheating, I think. But if you had done that, we'd have been through. So this one gives us rise to this. We can solve all the three problems that we talked about, and they have come up in other places. In fact, using this algorithm, the DNF counting that we have is surprisingly very fast. Surprisingly, I mean, I cannot explain how fast is that. Like the worm is kind of lying down almost. This graph.
I can imagine you're doing basically nothing, right? You're just flipping coins.
Exactly. It's like nothing is being done. Yeah. So what about the stuff? So we have solved this cleavage here problem, but there was a dependence on M. In PORS 22, we did come up with something what you were suggesting, having various layers of P and so on and so forth. It's a bit more complicated, and the complexity gets a log to the power 4. If you remember, it was no, but we don't have a M there. This proof is not that clean, so not as fun to present.
Is it still fast?
It's still fast, but again, this we have not implemented this.
Yeah, the fourth power starts biting at some point.
Yeah, fourth power starts biting. So this fourth power, we believe we can push it down to square, but the lower bound is just log. So there's a gap between log and square, and I think the reason is about we are somehow unable to marry the sampling algorithm and the hashing based techniques. It's like, I mean, for every possible. So remember that this inside this one of them is one of the logs is being taken away by the fact that we are storing the information of a single limit. So this basically you should read it as log cube omega number of samples are being stored. Okay. And we are unable to save on the amount of space.
But is it a different algorithm?
It's a different algorithm.
Okay.
It's a different. As I told you, this P always goes down. You cannot do that. You have to push P up sometimes. Yeah, so other thing is that Donald Knuth, when he saw this algorithm, he was very fascinated by trying to make it what's called unbiased. Unbiased is basically saying that expected output is same as the actual value. Our thing was not unbiased. Our thing was an epsilon delta guarantee. He really worked hard and came up with a very clever data structure techniques that solves it, except that it's hard to read that article that he has written.
So that's the next project now to simplify his deal.
Yeah, so that's the thing. So if something, yeah, I mean his ideas are very nice, a couple of them. So they can be merged to get a nice one. Yeah, I think that's all. I mean, there's some work going on, like this kind of overall concept of unifying the union of sets can be used in many places. Like for example, currently there's a project going on about estimating the number of strings of length k accepted by a non-deterministic finite automaton. I mean, it's basically becomes something like a union of sets part also. So, yeah, so reason I wanted to give this talk, one reason is that in case you guys plan to teach this F1, F0 estimation, here is an algorithm for it. Yeah, thanks.